Hello. Okay,
Be safe.
Thank you. You can. So, good morning, everybody. I hope you are fine. Are you fine? Thanks. Okay. Let's talk about determination in alpha and gamma ray spectrometry. I think that today you have to do this kind of exercise in the lab. Exercise at all, but let's see what happens. These are the contents of this presentation, how to determine peak areas, how to calculate activities, then something about the software. Which is in fact very simple. So you can calculate activity if you know measurement time, peak area, you know the emission data, and you know the efficiency. It's a very simple equation. However, I neglected corrections in this equation here. So, spectra. This is one of the spectrum taken from this presentation, publication. You cannot see, but you can later. Is the experimental data. Red one is so-called baseline. Let's look at this peak here. Determine the baseline. I mean, red or green. Complex answer, because from my point of view, both of these are okay. You have to typically this axis is logarithmic, so there is usually difference what is the baseline in principle. However, if the peaks are small, it might be large. In alpha spectrometry, there is no baseline in practice. And counts. For example, counts here can be taken into account for this nuclide, which is radium something, 226. What is an advantage of alpha spectrometry is that when radiochemical processing is done, and especially radio element separation, then the spectrum is very easy, very easy. So in this case, no radio element separation has been done because there are radium, radon, and polonium. So this is an example for uranium-235 and different enriched level. This is energy axis here. This is X-ray region coming. That peak shapes doesn't depend very much on the source characteristics, but in alpha spectrometry, source characteristics is very, of course, the peak shape depends on the energy a little bit, but not very much. Baseline may change, depending on the activity of the source. And some other things too. Right. This is one example. There are 3 nuclides which are curium. These nuclides here, here, here. At the very right side of the spectrum. Would you take this part into account in the area determination? Yeah, no. Because these are generated by soft photons, X-rays, perhaps gammas, electrons, positrons, etc. Area. Would take this part into account in peak area determination? Well, yes, maybe no. Depends how you do the peak area analysis. I will explain this more soon, but if you do region of interest analysis, as you did yesterday in the lab, then you cannot do that. But if you do peak fitting, perhaps then. Let's look at the basis of peak area determination. So there are 2 basic or main approaches, so-called ROI, region of interest, and peak fitting. In this method, you simply determine left side of the peak, right side of the peak, and the software automatically gives you number of the count. Or baseline here, not graph. background is a little bit different thing. What about peak fitting? Peak shape, which is practically Gaussian, as I explained yesterday, but there are some changes can be taken into account. In this case, I have taken so-called step function into account because the base here is higher than the baseline here. Both of these methods are or can be applied in alpha and gamma ray spectrometry. In general, this Roy method is okay if you have individual peaks. But peaks like this is 186 peak, so there is either or both 5 and radium-226. In principle, you can use a peak fitting method in this case. However, they are so close to each other that practically it's in this case not possible. Of an alpha spectrum in which there are two main nuclides, americium 243, 241, a little plutonium 2. So, how to determine the left side of this? You have to remember that in alpha spectrometry, the situation is usually that all these peaks are summed together. Because usually radio element separation is done. So it's not very useful to analyze the areas of these individual peaks. Here. If you are using peak fitting method, you have to know the peak shapes. Then it's possible. This is one example in our software known as Unisampo Saman. So it has in fact two softwares. Unisampo software search peaks. That's it. This Shaman code, it identifies the peak. It's a very, I think, very high-level software. Although the interface is not very good. But in case, this is 186 again. The software doesn't know that there is in fact two peaks because they are so close together. But software also plots automatically this baseline. And I can see, and you can see that, okay, there is something wrong here. So I can manually insert a peak here and do calculation. Okay. In this case, I added radium-226. Just an example. Spectrometry, the Roy method may be impossible to apply, and fitting is necessary. Yesterday we looked at this spectrum from nuclear bomb particle. What about this spectrum? It's quite difficult to analyze. It was obtained from this depleted uranium penetrator. This ammunition was used in Gulf War. So it's quite difficult to carry, but it is possible to determine activity ratio. Determine activity, we need to know peak area, but in these cases it's not possible because this peak continues there down, but we cannot detect down to zero pulses. When activity ratio into account this plateau and this plateau. I think that I already showed you this one, nuclear bomb particle again. Operation with German scientists from Karlsruhe research center. These are uranium particles of diameter about 1 micrometer or so. So they are pure uranium, nothing else. In the case of processed samples, there are several mathematical ways to fit the peaks. However, there is none for these sources in general. To fit also this kind of spectrum. This is residual difference between the measured uranium nuclides. I think this is a simulated case, and there are 3 nuclides here. So it is Gaussian, and then there are, in this case, 3 tailing components into account. Then you can really take all account when you determine areas, peak groups. What about this is normally quite normal case in environment because activities are quite often very low. So the number of peaks counts is very low. Okay, this is just an example containing same nuclides as in previous slide. You can see that there are 3 peaks, but how to determine peak shapes very accurately for peak tail. So it's sometimes radiochemical sample process. Not always, of course. These are the pictures from our software in gamma spectrometry. So efficiency, peak shape, and energy calibrations must be correct to obtain correct results. So in this case, There is a peak shape calibration. This is energy, this horizontal is peak shape as a function of energy. This is energy difference between linear calibration and true calibration, which was in this case second order polynomial. This is efficiency calibration that I showed you yesterday. We can get correct results. Take an example of an activity determination. Let's assume that we have radiochemically processed source having these nuclides. Data acquisition time, weekend, 3 days. This is seconds. Efficiency by using RC program. Area of this source diameter, source to detector distance, this, and the calculation is very rapid. Let's put this in addition to the data in the need to know the emission yield, which is obtained from the library. And in fact, 1, if you look at the data. Not Gauss. Decay corrections in this example because the half-lives are so long. Okay, as an example, these are the number of counts in these peaks. If you substitute number of counts, for example, in case of plutonium-230, alpha yield and efficiency, I got this one, 0.77 becquerels per sample. Very easy calculation. Very easy. But you have to know peak area exactly and efficiency exactly. So these two are for determining this. In our how to use tracers.
Amount of recovery that we are getting after the process.
Yes. Indeed, because chemical processing is very challenging. You never know how much, for example, polonium you get from the source. In this case, I contacted to you. They gave me these plutonium isotopes. You perhaps know that plutonium-39, 240, they are strongly overlapping, very strongly overlapping. For the source, but they didn't told us the activities. So my task was to determine the activities, and without traces. I made a measurement which is like this. Then I used our fitting software. In equilibrium must be always accounted for in the analysis. This uranium chain, these two are important. This part here and this part here. As I explained previously, we do vacuum packaging of the sample. You do put some glue or something so that the beaker is as tight as possible, because radon very easily goes out from the beaker. That's the point. And if the waiting time is 5 times, 6 times this, 3 weeks typically, then we can say that this nuclide, this nuclide, this nuclide, this, and these two, they are in equilibrium. Same thing holds here, but there is a problem. In some cases, I have noticed that, for example, plants may absorb thorium much more than uranium. So in original state of the sample, there may be no equilibrium. So there is no easy way to directly calculate the uranium-238. You have to assume equilibrium, but the point is this waiting time, decay time. So if you put the sample into a beaker, tight beaker again, and wait 6 months, as Avan has explained yesterday or day before, then there is an equilibrium. This is thorium decay series, and I have here 3 questions regarding thorium-228. It's difficult to determine by using gamma ray spectrometry. Do you have any ideas why? All right. Now, how it goes here. Thanks. Sorry, I'm very clumsy of using these. So you can see the energies of thorium-228. Okay, these are okay. However, this peak is very close to the lead X-rays. Sorry, this text is in Finnish, because this is I made this text several years ago for my colleagues, so that we do analysis always at the same time. So I collected information of each natural radio element and checked that there are no peaks close to the relevant peak. So in this case, the emission probability is 1.22%, which is very small. And in addition to that, there are less X-rays. These peaks here, emission probability is very low, and lot of other nuclei present. So we cannot analyze thorium-228 as such. Okay, question number 2. It is, so, do we need a vacuum packaged sample to determine 228 thorium on the basis of radium-224? Do we need? Okay, there are 2 options. Yes, yes or no, please. Yes, raise your hand. Do we need? What about no?
Does 234 radium give a peak? Give a peak, a gamma peak?
I mean that because 224 radium, it's quite easy. Let me show this again. And let's go. This is an example of radium-224 determination. It's this yellow peak here. And we can use this peak, at least in our case, we have quite good analysis program. So it's possible. But the question is, do we need vacuum packaging in this case?
No.
You say no? What do you say?
No.
All right, let's go back. Oh, so yes, the answer is no. Why?
Because it's not a gas.
Yeah, both are metals. They do not escape from the beaker. What about question number 3? Did you got this point?
Can you repeat your answer?
Sorry, I have to go here.
Can you please repeat your answer? Why it's no?
Okay, let's. Thank you for the question. It's very important to challenge me. So let's go back. Because in this case, when we want to analyze radium-226, we cannot use it because its emission yield is so small, and its peak is together with uranium-235. And it has practically only one peak. So we have to analyze its daughters. But then we must know the equilibrium. There is a problem here. There is a radon. And because of the long half-life, we must wait at least 3 weeks so that there is equilibrium between this, and this. These 2 are very easy to analyze. However, the beaker must be closed very well so that radon gas doesn't go out from the beaker. This is the case for radium-226. But, so the point is that this is the problem. It may escape from the beaker. Now, in this case, there is no gaseous, sorry, there is no gaseous nuclide between these two. So we can analyze radium-224 as such because nothing is escaping from the beaker because they are both metals.
Vacuum packaging not required.
It's not needed to do vacuum packaging in this case. We have to
need to wait for 3-4 weeks to attain the equilibrium.
To be absolutely sure that there is equilibrium. Typically, there is equilibrium practically always. But to be absolutely sure, then it's good. Okay, one more question. And this is related also to the equilibrium. So, radium-228, this nuclide, it's also difficult to determine because it practically doesn't emit gammas, or very little. However, this nuclide emits many gammas and very easy to determine. And its half-life is very short. So in this case, there is practically always equilibrium. But the problem is that, okay, we can determine activity of this radium on the basis of this. But this is difficult to determine, this one, because the emission energy is around 64 kilo-electron-volt, and the emission yield is very, very small. But can we assume that there is equilibrium between these three cases? Usually there is, usually. For example, if you want to analyze stones or rocks or these kind of things. However, what about the case if you are analyzing, for example, soil or sand? Water is coming from the sky, and it may happen that radium may dissolve in different way compared to thorium. So what we decided in Stuk that we do not report thorium except when we are analyzing rocks, stones, and some other construction materials. Because we are not absolutely sure that there is an equilibrium. Then we report only this one. And as I said to you before, all members of the decay series are in equilibrium, then all nuclides decay at the same rate. The point is that several processes, which might be biological, physical, chemical, geochemical, and other things, may influence the equilibrium. And this is very important to understand this. some slides about analysis software. There are some tools for generating alpha or gamma ray spectra, but not many. I showed you yesterday this ASI software. This is a tool for alphas. Now remember that to generate gamma spectra or alpha spectra, not to analyze. So there are high-level generators that are based on full Monte Carlo simulations. This means that practically all radius, all interaction phenomena are taken into account in the calculations. These are the examples of these programs: MCNP, GIAN4, EGS. There are, of course, some simplified codes, such as this one. What about the analysis of software, not generating the spectra? So one example is gamma vision and alpha vision. These are from Ortec. Prospect is a software package for data acquisition and low complexity analysis for gammas. It's a Mirion software. GSA is an open source software for gammas. Jenny, you have here, it is for alphas and gammas, as well as Apex Gamma and Apex Alpha. In Stuk, we are using Unisample Shaman program, which is running in Linux. But there are several other programs too.
Is Unisample Shaman open source?
No, unfortunately. In Stuk, we have developed these two software for alpha spectrum analysis because I don't like this ROI analysis. It is simple in many cases, but in difficult cases it's not. So we developed two different software, ADAM and ASI plus fitting, so we can analyze these kind of spectra. Well, if somebody wants, we can send, but this is operating in Windows, this in Linux. But this is it. Do you have any questions, comments? All right, if you don't, shall we have a break? Timing is now 10:06. Do you need a longer break? Avanes, is it so that there is tea or something?
Yeah, I think it should be.
All right. Is it so that we can go back 11:10? Is it okay? Thanks. You can ask these things outside. I will be there. there. Thank you. Shall we start, or what do you think? All right. Sorry? Yeah. Havana said that let's start within 2 or 3 minutes. Because somebody is missing here, some persons are missing just now here. So. I'm sorry to disturb you, but I think that we have to start now. Sorry once more. All right. In this presentation, I want to open your mind. So what does this mean? Karunakara said that you are not doing measurements very much outside of this building. Is it so? You are not very much doing measurements in the field. Is it so?
Direct measurements we
Yeah.
do not do. We bring the samples from the field and we do them.
Yes, samples.
Although we have a survey meter, the
Yeah.
sodium iodide survey meter,
Yeah.
which I can show you later. We don't rely on it much.
Yeah.
Because anyways, reasons are twofold. One is we don't have any kind of anthropogenic activity in India as of now, so it doesn't
Yeah.
make any sense to
Yeah.
do a survey.
Now I will tell you what we are doing in our institution regarding field measurements, which are quite challenging in some cases. Look at this one. After introduction, I will ask you, what is a laboratory? Is it a stupid question or not? Let's see. Then I will go.
Conditions are controlled.
Sorry?
The conditions are controlled.
Yeah, it's very difficult to do measurements outside. I mean, reliable measurements. You cannot carry your laboratory system into the field. So, what to do when you have to do field measurements or field sampling? And how to do sampling and sample processing in the field. Alpha spectrometry and gamma spectrometry in the field. Right. Different field measurement techniques. I mean, outside a fixed laboratory like this one. Maybe applied, for example, in the areas of nuclear security, nuclear safeguards, nuclear emergency, or like in this laboratory, environmental studies. So, in case of nuclear security, so there's a need sometimes, definitely not very often, to detect radionuclides that may be dispersed by using a dirty pump, for example. Just an example. And finding, for example, signatures. If alpha particle emitting radionuclides are used as a poison, you perhaps know the Litvinenko case. Do you know this Litvinenko case? You don't know. Around 10-15 years ago, Finnish government, in fact,
Sorry, 2008.
2008. All right. In fact, Russian government killed one of their spies by using polonium-210. The isotopes you measured yesterday in Alpha, but the amount was very big. So this poor guy died. If I remember it correctly, it was inserted in tea or some drink or something.
They have used two techniques. I don't remember. One is on the polonium-210 and one is on the nerve gas. It was Salisbury case. So the Russians used.
Yeah.
So polonium-210, I think they have injected into a drink. I'm not sure, but or they have put it into the doorknob.
Mm.
So
Yeah. So in nuclear safeguards, they are interested on mainly interested on actinium-like radionuclides. Of course, in a nuclear emergency, if an accident happens in a nuclear power plant, then it is absolutely necessary to do rapid measurements in the field and also sometimes in environmental studies. Now I really want to open your minds in the measurement. So, you know, radiation measurements in the field pose challenges, for example, sampling. And in the next slide, measurements. But the problem in sampling is harsh environmental conditions. In my mind, sampling should be planned so that sample processing is not necessary if you do the measurement in the field. And simplified means should be developed. And in case of a nuclear accident, there's no time to transport the samples in a fixed laboratory, which is possible locating far away. So, I think you do this way, but I think that this way is not necessarily the best way. It's much better to do measurement there, outside, and send the data that can be analyzed, for example, here. Challenges about the measurements. So, if you bring them out of a fixed laboratory, there are demanding conditions and detectors must be appropriate for field measurements. But if the detectors are already in the field, it is possible that you can get analysis results very quickly. Nowadays, in present days, data transfer is quite easy. But for example, 20 years ago, it was not easy. We have now quite good systems here and in Finland too. So, transfer data, no samples, if possible. So, in that case, we have developed a quite nice system in my organization. We are doing remote expert support in our building. Yankees calls this as reach back. So, all the data that you can see here, they are collected somewhere outside of our building. Alpha spectrometry, gamma spectrometry, dose rate measurements, pictures taken outside. So it's quite challenging task for this guy to analyze things. Problem for the field measurements is that very often it happens, at least in Finland, for example, if police or firemen do measurements, for example, in an industrial area, they don't understand radiation at all. You understand radiation. They don't understand at all. So, what will they do? They have some equipment. I hope this equipment can automatically send the data in our reachback center. Then the guy sitting there can analyze the spectrum, or if the dose rate is high, then he can tell to this guy that, all right, please stay away, now it's a dangerous radiation field close to this area. once more this one. What kind of analysis techniques can be used outside in a fixed laboratory? Or sampling techniques? Do you think are these good methods? Or these? Definitely no, because these equipment are quite heavy, very expensive, very sensitive. They do not stand rain or moisture or these kind of things. So, feasible for measurements in the field. Alpha spectrometry or gamma spectrometry. But how to do gamma spectrometry there? Let's see. So, field measurements can be done using different platforms, for example cars, etc., and different measurement equipment. And the point is now that here, at least from my point of view, is that what does it mean when we talk about laboratory? So, what is a laboratory? This is our normal understanding what is a laboratory. There are chemical things and different kind of analysis equipment. So it's situated in one place. Several sample preparation techniques are possible, and also different analysis methods. The one located here or in my organization. So, this is another option, movable radiometric field laboratory. It is built, for example, in a trailer. But the point here is that usually the measurements itself, they are not possible when the car or trailer is moving, like in this case here. It's a limited set of sample preparation techniques and also limited set of analysis techniques. And for example, Finnish Defence Forces has developed this kind of system. In fact, it contains radiometric laboratory, biological laboratory, chemical laboratory, all these things. What about next? This is our car. We call it a moving laboratory, and we call it sonni, which means bull in English. Why? Because these tubes here, they are air sampling tubes. We have a strange level of humor again. So, we are capable doing measurements outside when the car is moving. So it is of course not so heavily equipped compared with a fixed lab. But it is still capable of doing sampling and relevant measurements. And it's capable to send information to our headquarters. But mobile, you have your mobile phones. This guy has mobile laboratory. Well, the concept of laboratory, it's how to say, it's not very clear. Anyway, the system is located, totally system located here. There's a gamma ray spectrometer, multi-channel analyzer. This type of laboratory can be operated even by a single person, like him. So, Prerequisite is the possibility to send the measurement data autonomously to a remote location. However, if this guy is valid enough, he understands radiation-related things, then he can analyze the spectra in the field. It's possible. So, point is that there is no heavy instrumentation. Typically, gamma ray spectrometry. But in this case, he is operating now in situ alpha spectrometer system. So this is not a counter. This is a spectrometer. Autonomous labs. We have a sampler close to our institute, looks like this one. Sampling is done here. There's a filter. There is also a deposition equipment there. So this system can automatically collect the data. There are Geiger counters located here. You cannot see it well. There are also lanthanum bromide scintillation detectors, so we can get real-time spectrum from that system. Of course, limited set of measurements. Or there are not many options to do different type of measurements. Mainly gamma ray analysis. But there are some other options, like these. These are used, for example, by police if they are checking some dangerous objects. We have implemented, as I earlier told you, a sampler into a small UAV and a spectrometer. This is bigger one. This system includes very big sodium iodine detector. And finally, this remote expert system. So, in this laboratory, neither sample processing nor measurements are possible. So, do you call this as a laboratory? I don't know. I call it as a laboratory because we are doing analysis. So no sample processing, no measurements. The data can come from lab types mentioned in the previous slides, but data can also come from other places. For example, we can use maps, Google Maps. Do you know what is a waterfall picture? Perhaps you don't know. I will explain. This is very important in those cases when the measurements are done in the field and each measurement time, the measurement system is equipped in a car which is moving. And that car wants to see is there any object close to the street that emits radiation. So that waterfall picture is like that. So let's assume that there is a spectrum. looking like this one. But if the data acquisition time is, for example, 10 seconds, and you get 1,000 spectra, how they do or how they analyze in the reachback center these 1,000 spectra, it's not possible. However, if you visualize those spectra so that they are not looking this side to the spectrum, they are looking this spectrum, this is your eye. You are looking this way, and what you will see, let's delete this one here. They are looking the spectrum so that there is in fact, one channel or one bin, how to say it, time resolution, so that in each time, for example, in this case, the color, I mean the number of counts here is blue because the number of counts is high. This might be black. This is again blue, again black, etc., etc. In the next 10 seconds, same thing holds. You might get a different spectrum, like this one. Then at the next 10 seconds period, the point is this is a high level part, quite high level part here, low level part, etc. for this black spectrum here. So if you have multiple of these 1 pixel widths, then you can easily see that, okay, now the car is in some other position, and you can see that something is happening, for example, in this point. I don't know what's the point here, maybe perhaps this. So this is so-called waterfall picture. So you look at the spectra like this, not like this, as you are doing now. I hope you understand this. But this is just a way to present spectra according to colors, not according to peaks itself, but the number of counts. Any comment? Do you understand this? Yeah. Let's look at the sampling. What do you think? Is this possible in the field? I mean, you should carry strong axes, for example. No, it's not a good idea. No. However, the point is that if you simplify sample processing in the field, this simplification means fine-tuning. So you minimize the sample processing. It is quite often sufficient. Major changes are not needed for the sampling. Typical example is air samples. If you select sampling material properly, for example, if you are analyzing alpha spectrometry in the field, which is possible, it may be better to use membrane filters instead of glass fiber filters. It depends on the case. Filter type is essential thing in alpha spectrometry. Here are some examples for alpha measurements. You can put the filter directly into the vacuum chamber if you need a vacuum chamber, because it is possible to do the measurements without any vacuum. Wipe samples. This is a piece of uranium. I took samples. This can be put to the detector here, to the vacuum chamber. And then some simplified processing system. This can be used, for example, in a car. It's very easy to put there, for example, an infrared lamp. And then you can put this beaker also in this chamber. What do we do in the measurements, in the field measurements and sampling? So we laminate the filters. You know that filters are like this one. So it's when it's raining or difficult conditions, windy conditions, this is very difficult to operate. However, if you laminate the filter so that it's quite stiff, and there's a hole through which the air goes, then it's easy to do sampling in the field. And this filter can be placed as such into a vacuum chamber or into a gamma ray spectrometer. And the use of battery-driven samplers, like this one, no external electricity is needed. So there is no major filter manipulation. Only filter cutting, because maybe you can see that in this filter there are 3 holes here, here and here. Why 3? The point here is that this 3-part structure allows the use of complementary and simultaneous analysis techniques. So we can put that part of the filter to the vacuum chamber, that part of the filter to a gamma ray spectrometer, and that part of the filter, if we want to analyze, for example, individual radioactive particles. So we can do 3 different analysis techniques for the same sample, very easily. We just cut the filter in 3 pieces using this kind of system, which is very easy system. We put the filter like that, then do this, take out of the pieces, and substitute them to the measurement system. Another simple cutting procedure, but not so handy as the previous one. So the edges of this iron cylinder, it's very sharp so that it can cut a piece of the filter. But this is not handy. About liquid samples. If you take a small sample from sea or lake or river or whatever liquid is, you can take a few milliliter liquid sample using a pipette, for example, put the liquid on a beaker. You can, in some cases, insert small amount of another type of liquid to remove the surface tension. This is possible. Evaporate the liquid so that radionuclides stay there, and put this beaker to the vacuum chamber of an alpha spectrometer. And you can get out quite good spectrum. Wipe samples. For example, here is one of my colleagues doing, in fact, polonium sampling from the walls of our garage. It's an accumulator driven sampler, and there is a nozzle here with a membrane filter. This is another system. You can take samples from soft surfaces. IAEA has developed a impactor here, which does the same thing. You can take the sample like that. This is a volcano picture. Not very relevant in this case, but anyway, it's a good visualization. Let's look at alpha spectrometry in the field. As I told you, several measurement techniques are available for air filters and other samples too in the field. Gamma spectrometry, alpha spectrometry, beta counting, imaging techniques, I mean digital autoradiography, dose rate measurements, etc. In our car, we have in the roof, somewhere here, there is a high-purity germanium detector for nuclide identification. There are two sodium iodine detectors here, one in this wall and in an other side of this car, one detector. Inside the car, there is also a high-purity germanium for sample measurements. And we also have alpha spectrometer here. In this case, there is only one alpha chamber. So I think that high-resolution alpha spectrometry is possible in the field conditions. Not in open sky, but if you install the equipment into a car, it's possible. In this case, there is laminated filter here, inside the vacuum chamber. So, our Sonnicar Bull, so there is a MCA here, alpha spectrometer. This is so-called NIM rack. Power supply is here. And in the back of the car, we have a vacuum pump. Right, this picture again. So radon concentration in the garage air is around 100 becquerels per cubic meter. So is it possible to detect polonium by using non-destructive alpha spectrometry? So polonium is present on the surface, not in the air. So this garage was quite old, so that there is radon in the air. Radon disintegrate into this polonium, and this integrates rapidly into these metals. They are small particles, and these particles are deposited on the surfaces. They do not stay in air. They will deposit on the walls. All right, let's see. It is possible. So, we used a membrane filter, and we found out that it is possible to detect polonium in this level. There are some other nuclides too. And in this case, you can see that the peaks are very sharp, very, very sharp. Suppose that in that wall there might be plutonium isotopes, americium isotopes, a lot of other radionuclides. Then you might have a very good spectrum in one short sampling. So, this is the sampler that we put into this small unmanned aerial vehicle. The size was this. So, this is my very old car. I was a little bit embarrassed when I drive this car because I put them here and tested how this sampling system is working. So we used different type of filters, and I used non-destructive alpha spectrometry. So the filters which are inside here in these two samplers, they are membrane filters which are put into the vacuum chamber. We tested several filter types. For example, these two are glass fiber filters. We can quite easily polonium 214, but using fluoropore membrane filter, it's a quite good filter, I think so. The peaks are very thin. So these measurements are really done in outside air. Let's suppose that there is plutonium, for example, in the air, and you have to do quick analysis. I think it's a good, not a good system to do sampling like this, but sampling could be like we do in our Sonni vehicle. Does this open your mind at all? I hope so. All right. We have an alpha detector here. So, is it possible to measure quality alpha spectrum in the field conditions, in normal temperature and pressure, and also in the laboratory? Well, it is possible if the sample is thin, but if the sample is thick, we might have some difficulties. But there is another possibility that I investigated around 15 years ago. So let's assume that there is a source, and let's put a honeycomb collimator in front of the alpha detector here. So these are the walls of this honeycomb collimator. What happens? Goes this way, but doesn't go to the detector. So this way, it collides to the wall. This case, it goes to the detector. So what happens? Original spectrum is like this one, with these three isotopes. However, if we collimate, we get a good spectrum. But perhaps you already realize that there are some bad things too. Bad thing is that we lose efficiency. So we do not detect these alphas, we detect only these, which are going quite perpendicularly to the detector. But this is good when we need to identify nuclides. There is a comparison. Energy from 4 to 10 MeV, these are normal nuclides present in air. This spectrum is from a ideal sample. This one, I think it's a fluoroporefilter in this case too, quite thin. Vacuum chamber. If you do not use vacuum chamber, the spectrum looks like this. However, if you use collimation and also NTP conditions, the spectrum looks like this. So it was for me it was a surprise that it is possible to get high resolution alpha spectra in normal air conditions.
Why there is staining to the right side and 2.2 colony?
This is because of it is mainly because of this nuclide, Bismuth 210. It emits betas, and because this is very short-lived, betas are in coincidence with alphas, and that's why there is right side. I have written a paper 20 years ago. It's explained there. All right. So we have developed a viable equipment which is known as Adonis, this one, for in situ alpha spectrometry from smooth surfaces. So we can measure by using this system. This is the alpha detector itself. We can measure alpha spectra in the field conditions here, in this surface, whatever, and we get very good spectra out, very good. So we get rid of NIM electronics We have battery-driven multi-channel analyzer in the backpack. It's a computer-controlled system, as you can see here, and it is able to send the data to a remote location, to reach back, for example. Very handy system. It can also include gamma or even neutron spectrometers. Well, neutrons are not very often used in the field measurements, but basically. So this guy is really measuring alphas from this surface and able to automatically send the data. And again, this picture. So if this person, for example, is using his car or bike and has a gamma spectrometer with him, so it's possible to send data while biking or driving the car automatically. This is one of the pictures that our reachback center can see in real time, no delay. Okay, some seconds delay, of course, but it's not significant. This is alpha spectrum. This is, in fact, beta spectrum detected by this system. So this system detects also betas. And we can locate, for example, radioactive sources if it is located in some of these places. In fact, we are using this system normally. For example, if Trump, future president of USA, will come to Finland, our team is using all of our systems to check that, okay, roads are safe to go, etc., etc. I don't know every details. We are doing work together with police. Now I show you only a few slides regarding in situ gamma spectrometry. I think when you are using measurements outside, you are using systems like this. So there is a tripod or trolley holding the detector. Distance is 1 meter above the ground. Handheld system, yeah, all right.
But measurement is usually 1 meter.
Yeah. So do you automatically send the data somewhere, or do you collect it only locally?
I have not seen. I don't think so. It has an. Memory disk.
Yeah.
We can retrieve and send it.
Yeah.
So the system itself would not have a
Yeah.
direct data.
Yeah. All right. It's, of course, a good system like that. So the goal of this system is to determine soil activity concentration. It is usually done by detecting natural nuclides, sometimes detecting cesium, as a function of soil depth. And in case of a nuclear incident or accident, we can detect fallout or deposition. So why I am always talking about these accident or incident things. The reason is that in my organizations, we have to be prepared for these kind of things. For example, if Chernobyl-like accident happens, so we have to react very quickly. That's why we have developed all these strange systems. So, in this measurement, we have to take geometry into account 1 meter above ground. Normally we have to assume uniformity of the surface, but form of terrain, vegetation, surface, roughness, trees, etc., must be taken into account in some cases. All right. So, system, if you want to analyze becquerels per surface per square meter, then you have to do some calibration, and it's very important. I do not explain this. You can check these slides later. But the point is that you can start the calibration by using point sources located at different distances from this symmetry axis. So we have used different equipment. This is a military equipment here. For example, after Chernobyl accident, it was possible to detect deposition of cesium. There is a very big scintillation detector and also high purity germanium detector in the helicopter. All right, this is it. Now, my intention was to open your mind to see that there are a lot of different things that can be done in the field measurements. Measurements are quite challenges if the conditions are bad, but it is doable. Thank you very much. Questions, comments? Deep silence.
Deep thinking.
Yeah. Is it so that we have lunch at 1 o'clock?
Yes.
Is it possible that I could show you how our system works with efficiency transfer? Because efficiency transfer in gamma ray spectrometry, I think it's a good system, and there is a software. I will give you a link, or Karunakara will give you a link, that if you are interested on efficiency-related things, because the user interface is very simple. It is used by using Excel, this FTRAN software. I can show it to you, but not now. I think that we should have 20 minutes break. Is it possible? And we come back 12:30. All right. Thanks. Many different. several papers and my name. Then you can find the papers and if they are not accessible for you, I can send you the papers. I don't remember. A bad memory. I don't remember numbers. But I think it's very sensitive. Very sensitive.
What you take when you feel the instruments, what you take in the field, what you have in the laboratory. Like, is there a difference?
Yes.
But it is for a linear path. This is non-linear. This is logarithmic programming.
All right, let's start talking about the efficiency transfer things. When I downloaded this software from net, it's freely available. I found out that there is a version for GIAN 2, which is practically the same version as this one, which I use here. I think that the only difference is that this system can give information to GIAN or get information back to GIAN. I don't know exactly. All right, this is a user interface is more like same as in ASIS software, so it's very, very, very easy. So there are only three windows: detector window, source window, and finally the efficiency window. Let's look at the detector window. Detector is described here. So there is a bulletization, or might be bulletization. There might be absorber at top of the detector. This is detector window here. There's a gap between the detector and the window. Housing is the thing that you see when you look at the spectrometer, etc. But let's go here. So the only thing that you need to put for detector information is this. And if you change this information, you can store the information. For example, in this case, the crystal diameter is assumed to be 8 centimeters and thickness 3 centimeters. There is no bulletization, dead layer thickness, side layer thickness, etc., etc. So these are very simple input values. Once you do it, it's that. You do not need to change it.
But do we get these values?
Sorry?
Do we get the values of dead layers and side dead layer?
Well, to get values for the dead layer, it's very difficult because usually the Mirion or Ortec doesn't give you that information. But I said to them, when I last time bought my detector, that, okay, I will not buy your detector if you don't give me this information. Because the price of the detector is, in Finland, 100,000 euros, very expensive. So they gave me this information, but they said that, Roy, please don't give this information to other, don't publish it. I don't know the correct level of dead layer in this case because this is probably not one of our detectors. But this is just an example. Dead layer is typically very thin, some micrometers only. Okay, let's go to the source. Now there are two sources, which is standard here, and the sample itself. Now remember, this is our standard, this one. As I told you, this is so-called T20 calibration. So I don't remember exact diameter of our sample, but it is around 5 centimeters or 7 centimeters. I put there container diameter 5 centimeters. And container bottom thickness is 1 millimeter, as just an example. I have there water, or almost water. There is some acid there. And 2 centimeters is the filling height. Very easy, very easy. Now, about the sample we are measuring. What about if we are measuring water sample, but thickness 1 centimeter? Everything is same here. Let's look at the efficiency curve. This is some efficiency curve. These are the efficiency values here. This is the energy. You can put uncertainty there. And please, this is Excel. You can change the axis as normal Excel. Okay, let's do the calculation. I hope it works. No. It's not working.
Standard efficiency is 0.12. Sample efficiency is 0.15.
This is not the sample efficiency, this is the standard efficiency.
Okay.
But why can't I see it? I don't understand, sorry.
It's giving the values.
Yes, it gives the values, but I want to see the values here.
It gets below. It should be in chart. Right. So,
Can you? I don't. Because when I click here, it should show the value. Okay, I will start it again. Efficiency transfer. Okay. Now I change only these things. 20 millimeters. Let's put here 50 millimeter diameter, 1 millimeter thickness of wall, bottom. Let's assume water. Sorry. This one. Now the sample. 10 millimeters. Exactly the same beaker. 1, 1. Okay, now it's okay. Now I think it should operate. All right, now it's this one. I select changed logarithmic axis here, so it's this. Let's put the minimum value 10 kilo electron volts. So, if the sample is,
How you got these values? If you
well, this black is the, how to say, it's the standard value that I very carefully have been done. So this is efficiency transfer if I use a sample with 1 centimeter thick. We can very easily change values here. Let's assume that the sample thickness is only 1 millimeter. Do efficiency calculation again. It's like this, in this case. Normally, what I do is to put efficiency values as 1, because it's more easy to check relative values. All right, now this is the efficiency, this black curve here. And let's change, for example, this number to be 3 centimeter thick. Calculate it again. Now it's easy to see what happens. All efficiencies are 1.
Two different matrices. One is water.
Sorry, I have to go close because of. Yeah.
So if I want to use two matrices, now you have used water in both the cases.
Yeah.
For example, I want to use water for standard,
Yeah.
understand, and for the sample I use sand.
Something like, yeah, all right, let's see. I will change the number format here, sorry. Number, Excel is sometimes quite number. Now it's more easy to see. Okay, let's change. Let's put the same source height, but now it's not water, but something else. Let's assume that it is, I have done new materials here. Let's assume that it is sand, but now in this case, density is 1. This can be easily changed. But let happens. Let's see what happens. Very easy. Very easy. Now, you doesn't anymore do any standard measurements. You just do this calculation. There is a Gini version.
Can I select the density of the material?
Yes, but not in this interface. I think that this interface is a little bit clumsy because I can't select the density here. The material properties are, in fact, got from NIST made so-called XCOM program. So it belongs to this Extran package. And there you can do different materials. But you have to know something about your material composition. We can change it very easily. Let's try this suolavesi. It's salted water, like seawater. It has salt. Let's do again calculation. Effect is this. If I assume that thickness is 2 millimeters, do calculation again. New resolution is the this one. So, very simple system. But I suggest you to download this FTrans software and do it yourselves, because it's a way to understand what happens. If you have a different beaker size, for example, if you do not want to use same kind of beakers as you normally do, it's easy to change. For example, container diameter. If it is, let's put it 70 millimeters, and do the calculation again. The result is this. Very easy. Do you want to see other calculations? Please give me suggestions.
How to download this software?
I gave Karunakara the website.
So I
Yeah. Do you want to have more calculations? For example, let's assume that we have exactly the same source filling height. Let's assume it's also water, but the beaker bottom thickness is very thick, 5 millimeters instead of 1 millimeter. Sorry, can you?
Can you please show one sample for air filter?
One
One sample for air filter. Filter sample.
air filter. So,
yeah, okay, no, I tell you there's no problem.
so in case of air filters, we can do this software. So the point is that source filling height, in that case, its filter thickness is very small. It's, let's say it's one millimeter thick. Let's assume that. All right. And if we are measuring it in the same container as in the case of standard sample, but the material is not water, filter material is not water. Let's see, is there any appropriate materials? Silica. Glass. Please know that one thing is very important if you are doing gamma spectrometry in case of low energy gammas. Then elemental composition, what are the elements, are of importance. You should know something about the composition. At higher energies, the composition is not relevant. Higher means more than 100 kiloelectronvolts. But let's say, for example, at the energies of lead 210, then elemental composition is practically necessary. You have to know something, but you can easily assume that all plants, for example, have same composition. But the composition is, of of course, different if you're measuring soil samples. The composition may vary. Is it organic soil or inorganic soil? I mean sand. That's the only, how to say, difficulty here. But it is only for low energies. Very handy system. I have learned a lot of using this system. And you can easily transfer this data to Excel. Just Control C and add. Now you can print the pictures here. The problem here is that it only shows one efficiency per time. I don't like this, but I can do it like this and print data here. All right, this is it.
Good.
Shall we have a lunch?
Yes.
All right, thank you very much. Can do more simulations. What's the time now? Let's see. Yeah, 7 minutes.
Please explain from the standard how we are going to sample, how that extrapolation is being done. Is it by some analytical or some other way that you are employing here?
In this case, the efficiency, it was, we call it as a raw efficiency. It's determined for each nuclide separately. Normally, we use a smooth function like that, so we make fitting. So it's the original efficiency that is not present here just now. It was a little bit, it was varying a little bit, yes.
Yeah. No, my question is, that is for the standard, correct? That is
So-
a measured values. Whatever you are giving it for the standard
Yes.
is a measured. My question is, how you are extrapolating it to sample?
Extrapolate to,
Sample, right? That's the reason you are, when I am giving the standard things here, I am extrapolating it to the sample, right? That's the meaning of the transfer. That's
Yeah,
what I am
yeah,
understanding.
yeah.
Efficiency transfer means
Yeah.
I have the values, the measured efficiencies for the
Yeah.
standard.
Yeah.
Now I am going to go do it for the sample.
yeah.
Isn't
But
it?
this red one is for the sample.
Yeah.
Yeah.
Yes. No, my question is, these are analytical values or
You use
how
any MCNP,
yes, how you got these values? That's my question. For a
any
standard,
MCNP
you have to
simulation,
measure it.
something like that?
Well, it's a simulation program, this
Acha,
one.
oh, that's what we are asking.
Yeah.
How it was done?
Yeah. Yeah, it's a simulation, not full Monte Carlo simulation.
Okay, right. That's
It's a little bit, because I haven't done this software. It's one of the Belgian scientists, so-called Tim Wiedmar. He has done this software. It's not a full Monte Carlo.
Okay.
If you are using Monte Carlo ways to do these calculations, it's a very tedious way. But this gives quite good results. It has proven in many scientific publications.
You have validated it, sir.
Yes, we have validated it.
No, because we do with Monte Carlo MCNP.
Yeah.
Yes, sir. We do this exercise,
Yeah.
measurement, like calculation of the efficiencies,
Yeah.
estimation of the efficiency using MCNP code.
Yes, you can do it by using MCNP.
Exactly, sir. But
Yeah.
anyway, everything needs a detector geometry.
Yeah.
The dimensions and all should be there. Yes.
Yeah.
And oh yes, again as you told, it's a manufacturer who has to give the dimensions.
Yes, the point of using MCNP is that you have to know detector characteristics very well. And usually you do not know all the characteristics of the detector. But in this case, when there is efficiency transfer, detector characteristics are more or less cancelled because of the transfer, because of the transfer process. You should read this from the literature. It is explained there. So and it takes some time to do those Monte Carlo calculations. This is easy because it's a second or 1 second.
So quite fast.
Yeah.
Monte Carlo, I think one energy.
Spectrum. You have to give the feed the spectrum, and you will get the efficiency with respect to the energies. That's it.
Yeah.
Okay, sir. Thank you.
Thank you very much.
All right. All right. Thank you.
I understand that Mr. Avanish has shared this formula with you, and if not, you can note down. MDA, minimum detection activity or minimum detection level, is one of the very important parameter which is used in any nuclear any radiation detector. So if you want to publish a paper on your measurement, you should always report what is the minimum MDL or MDA of your detection system. So reviewer will always ask what is that, and you should also be knowing what is the background of your detector, because these are the important parameters, as I said in the beginning of the session and the previous practical session. So what is the important parameter is MDA, and this what we use is IAEA formula. So International Atomic Energy Agency has given, of course this is derived from basic statistics. You can get it from any statistic. book also. And nowadays, across the world, so in majority of the laboratories which does this environmental radioactivity measurement, they use this formula. MDI is equal to 4.65 into root B. B, what is B? B is the background of the detector. So suppose if you are using the high purity gamma spectrum, you should take the background in the under that peak. For example, I'll tell you the peak, there is a peak of 609, bismuth 214. You know which region of interest, number of channels you have used, starting channel, ending channel. And for the same region, you should note down the background. And this of course, to subtract from the sample spectrum. So that into efficiency, A, abundance, counting time, and weight of the sample. So you should always report the minimum detection level of my detector for a sample mass of 250 gram is this much, or a sample mass of 100 gram, or a sample mass of 5 gram. You should report what is the MDA. And this is how you calculate. So those who have not calculated it yet, and this is applicable for all the nuclear detectors, okay, be it alpha spectrometer, be it high purity germanium detector, sodium iodide detector, or zinc sulfide detector, or the liquid scintillation spectrometer which is used by ARIA, everywhere, okay, for all this detector it is the same. So this is the formula you use. So in yesterday's and day before's experiment, you have learned how to evaluate the gamma ray spectra, how to take the counts, how to subtract the background, and how to calculate the activity. Now today what we will do is, those who want to know, yesterday we have put some sample alpha spectrometer, this alpha source or alpha radiochemical separated polonium-210 plated silver disc onto the alpha spectrometer. So it is there inside the alpha spectrometer. Now the spectrum is acquired. Those who want to see the spectrum again, you can go there and note down the counts and calculate the activity again. And today afternoon you have two tasks. You go to the sodium iodide detector today and find out adjacent to the high purity germanium detector there is a sodium iodide detector. So you see the spectrum of the base, both the spectrum. So what Avanish will do is he will show the HPG spectrum and he will show the sodium iodide spectrum live acquiring using a uranium-230 or thorium-230 to source. Let it acquire, or you can show them the cesium or cobalt source. So this, anything is okay. Cesium source you put, it will be very fast. You should appreciate that what is the resolution, what you mean by resolution, how the sodium iodide spectrum look like, and then for evaluation of the activity of the sodium iodide detector, the activity formula remains same. Only thing is how you evaluate the spectra. So there are, since we use advanced Genie software, this software also gives you the Compton suppressed, Compton corrected counts. That is area, integral and area. It is a highly advanced spectrometer. What you are doing, you have done yesterday, day before yesterday. The spectrum, the software is able to do it automatically. So you create a batch file. So if you create a batch file, it will start counting at a particular time. The time you set, for example, today 10 o'clock you want the spectrometer to be counting the sample, start counting. So you can create a batch file. It will start at 10 o'clock. It will count next 24 hours, 48 hours, whatever you set. Then it will evaluate the entire spectrum. It will correct the background. It will search the peak. It will do the, if you feed the mass of the sample taken for analysis, it will give the final activity. So many becquerel per kg it will give. So it is so highly advanced software. But then why we have asked you to do, because all of you may not have the same software. So you want to do it yourself after you go back to the lab. So that was our objective. If you want to see that option also, we can probably try to do it tomorrow afternoon. how we do it automatically with the advanced software. It is up to you. And today what we do, we are giving you a set of sample, okay, which are in different geometry. We have recently received a set of sample from IAEA for intercomparison, international intercomparison. So we already finished this assignment. We submitted the data and all our data was accepted through. So what we do, we give the same sample to you. We know what is the activity of individual radionuclides in this. And we have standard reference materials also for this in the same geometry. Adu kuda illi untu. Reference idradu standard kotidradu. This is standard, this is standard, this is sample. So this again contains very low activity. So if you start counting today, it will finish tomorrow. So why we give for this reference material, we give you already stored spectrum. And for the sample, either we can give the already stored spectrum or you can put it for counting today and get the counts tomorrow. It is up to you, as you wish. But it is already counted, but you should evaluate the activity for both the samples. This as the reference, this as the unknown sample. Take this as an unknown sample, we will give the reference spectra with this and you put this as a sample, let it count. Okay, you see the counting, how slow it is, how fast it is. And meanwhile, you take the already stored spectra for this, do the activity calculation. And at the end of the day, let us find out whether you have evaluated correctly, whether you are getting the target value, okay? And tomorrow morning you come back, by that time this will be, the data, new set of data will be ready, spectrum will be ready. You do it again if you want. So that is the one objective. And second is, we have a set of filter papers.
One is black, one is standard, one is CC,
Yeah.
one is structure.
Yeah, one is standard.
This is blank.
Yeah, we have a set of filter paper, one is blank, which is expected to have zero activity, background. And we have another filter paper with the reference, where the activity is already spiked. And we have one unknown. Okay, this also you can put it to counting in another detector. Meanwhile, this reference standard reference material sample spectra also we will give you, and you take the other one, evaluate the activity. Okay, and we have another set of,
Small geometry.
yeah,
Thorium and uranium.
yeah. So we have been talking about different types of geometries. So you can see that we use reference material in various geometries. Spectra are available for these also. So you can recall this from the computer, and if you wish, you want to calculate. You can also, for example, you take 250 gram of as the reference material, and this is the unknown, and you evaluate, and you will find that for the geometry which you have used for 250 gram, if you use that as the reference spectra, and against that if you evaluate the activity for this, you will find that it will be off. Okay, so you can do all these things whichever way you want. So I recommend that first you finish this assignment. You can split yourself into two groups. One group, let them do this water sample, other group you do for filter paper, and tomorrow you can reverse it. Okay, and meanwhile we have prepared one polonium sample plated onto the silver disc without tracer. Is it not, Arya? Yes. Without tracer. That is also ready. If any of you want to see the gross counting technique, gross alpha counting technique, so that you can take that sample, take it to the gross alpha counting system, put it and count. That also you can find out. You can find the efficiency of that. You can, because the activity is known, and you can play with that gross alpha counting technique. That is also possible. So target is one batch should finish this, other batch should finish this. Over and above, if you have interest, go to the alpha spectrometer, note down the counts again. Go to the bulk gross counting system for polonium and check that one also, right? Any doubt? Any clarifications? Okay, clear? My friend from Manipal is in a deep thought.
I think I have a friendly guide here.
You are?
A friendly guide here.
Okay.
He is much better in the subject.
Okay, oh, I see.
Back page.
So,
He's
you,
scribbling down very basic.
so you feel you are safe. He is scribbling down, so you will join him, you are safe. Okay. Any input is required from our side? No. Then Avanish, give them one batch, let you go to you take this water sample and count, but be careful. Be careful not to ensure that it doesn't fall down, because in case it falls down, everything will be contaminated. So in all the low background counting laboratory, utmost care has to be taken to avoid contamination. Okay, even a drop of sample, maybe it is background sample, still you do not know. Utmost care has to be taken to ensure that there is no spillage. Okay, that is one thing. Right. Okay. Okay, good luck.
Yeah. Yeah. Oh, ನೀರು ಒಂದು ನಿಮಿಷ. ಸೇಮ್ ಯಾವ ಹೌದಾಗಿ ತಾಯಿಗೂ ನಾನು ಬೇಲಿಸಿ. So initially we'll start with the explanation between the. I hope you already know the sodium iodide and HPG differences. I have showed it in the first day. So even then I can show you a cesium spectrum at the later stage. We can develop it right now if you want, or I can do it later also. So let us start with that. Basically, yeah, just give me a cesium sample. So I'll keep all the three together. So let us see.
3 together?
Like 2 together. Cesium and cobalt. Yep. So let us see how. One ನಿಮಿಷ. Yeah, it is a well type detector. I had shown you, no? So I've kept. I will show you later. Okay, so I kept the source carefully. I have to close it. It's very heavy. It's lead. Okay. So now what I will do is I'll just show you the spectrum first. Yeah. Okay.
Is that gap in the lead setting doesn't bring any problem in the counting?
Not much because we correct for background, no? Actually, it was not there, but
Because then the K40
yeah.
in background will be much greater.
I understand. Actually, what happened, there is just a small gap between the things, so we are trying to fix it. Medium communicating or not? You have to check. Medium is communicating on. Medium service manager is on. Switch it off. It's not responding. So I'll just it down. No, so I'll have to restart it. Yep. So just restart. So actually, there is something called as VDM. So that has to communicate. That is the communication link between the your MCA and the setup and to the PC. So if
Then the video problem is again.
yeah, medium. No, it is only with this analog. The digital systems are very much seamless. This one is 30, I think 16K. It is 16K.
And the other one?
This is 32K. All others are 16, this is 32. So we'll just wait for the system to on. So first I will just prepare the sample. This, how do you want to do it? Do you want to count the sample yourself and take the results tomorrow, or is it okay you can, if I give you the counted spectrum? Because it's again, it's the same thing. It takes a long time, so this doesn't have much activity. So I will show you what exactly these samples, how do we get it. So this is the basically the sample that IAA gives us. So what they do is that they don't tell anything. They just give the values of standards. Okay, the standard, where is special? No, nobody's there, so I'll find it out. So you have, they'll give the value of this sample too. They will give value of one swipe sample which has the activity, and then they don't tell us anything. So they'll say that you have to analyze and you have to give us the results. So before keeping it in, I have to ensure that it does not spill. Correct? Give me that IAEA report 2024. So let us just make sure that it does not spill. Okay. So this one works. If you want, you can just remove the air from this, and now your sample should look something like this. So what if there is some leak here, it should get contained here. So I'll show you the report how it comes. So this is a sample, the paper that they mail us. So you can see that they have sent us instruction to participants. So you have spiked water, this is QC, meaning quality control. Then you have sediment bauxite that I am not giving you right now. Then you can see 4 spike samples, in which 5, sample number 5 over here, sample 5 over here is our sample that we have to analyze. Sample 6 is QC, quality control sample for cesium 137. Sample 7 is QC for strontium 90, that we cannot do by gamma spectrometry, we have to go to beta spectrum, so we will avoid it. And sample 8 is a blank. However, that's already explained to you. So the sample 1 and 2, they will give sample preparation, how they have done it, and you can see that radionuclide content in water too. Americium, barium, cobalt, cesium, tritium and strontium. So in this, whichever is applicable to us, we have to take, they have given the activity concentration in becquerel per kg, and they have given us a reference date. So the reference date over here is 2024-11. So from here, from the counting date, we have to back calculate and find out the activity on so from that date to calculated date we have to calculate the activity and then we have to calculate it, and sediment 3 4 is not applicable for us. So sediment 5 samples 5 6 7 8 they have given us cesium 137 activity, and 7 is not applicable in this tree because it is strontium 90, can't be analyzed here. So these are the only thing. Then they will give a end date and some related informations on the sample, the requested reports per sample in what on what units they require. So they have said becquerel per kg for most of this. Sample 5 it is becquerel per sample. So that's it. So these are all evaluation matrices. How they evaluated, and if it is A, it means accepted, trueness and precision is accepted, N means not accepted, W means trueness is accepted but precision is not accepted, so it would be warning, so you have to correct. So we have got all almost all as accepted, so most of them are as accepted, so not most, I think all. So that's how we can say that our results are standard. Okay. So that's all about it. So I'll just show you a spectra before starting with the counting of the sample. So I hope you know. Do you want to operate it? Yeah. So I'll just sit here just for the sake. So
This gamma acquisition.
yes.
Gamma acquisition.
Yeah, we have renamed this title as such. Okay, now what?
5.
Yes.
Open data source.
Yeah.
Detector.
Yes. And
Select the detector. There is only
Now
one.
it's detected.
yes,
Then click open.
open. So the detector is open now. Detector should come. Okay. So this is a spectrum that I had kept for which one? I don't know. Just find out what spectrum is this.
So there is, it is K40.
1446, K40.
It is K40. Okay. So I'll save this spectrum. Save as okay. Save it as RGK. Okay. So now I've saved the spectrum. Now you have to analyze the spectrum. So how do you do that?
We have to open the spectrum file.
It is spectrum and that is already open.
ROI we have to.
No, I have to start calculating. So what should I do?
So you want to select the display?
Acquire setup. Okay.
Time.
Time. Yeah.
We have to change it.
Okay. How much you want to give? This is a high active sample, so we'll give 100. 100 is enough. Okay. Next, what will you do?
MC first channel we have to select.
No.
No, just start.
Start
Acquire
only,
it.
no?
Just click start in
Start.
the
Start.
No.
Data source is there.
Everything is set. High voltage we not to change. There is one thing you have to do. Just
Take that.
Clear the spectrum.
Clear.
yeah.
Clear the spectrum.
Clear the
These things we have
Just
to clear.
there is in acquire.
clear
Clear
data.
this one.
Yes.
Clear data. And ROI.
Yes.
Oh yes. Everything.
You click clear.
Because you are that is old data. Now you want new data. So you don't want old data to win. Now start.
So start.
Start.
So the now new peak, a new
Yeah.
spectrum will come.
Yeah. Start. See. So that is okay. You have seen how narrow the channels for cesium was already, right? So you can see that here, this is what? Wait. This is 661, correct? Yeah, 661. So it is cesium. Can you see the channels over here? This is the control R. So you see the channels. So this channel, this energy over here is what? 785. And this energy over here to the other end of the spectrum is 552. So between that, if you get any other peak, it will merge with the peak. See these two peaks, you remember how it was shown in HPG, don't you? It was very spacious, very well distinguished. Now look at this. It is 1180 and 1332. It's all nearby, very close, like only one channel is separating both of them. So counts from this can spill over to this, counts from this can spill over to that. So that resolution is less. So that is why we prefer HPG. So this point I think it is very clear now. So we don't have to worry much about it. Yes? So here we have kept both the peaks, both the sources, cesium-137 and cobalt-60. So you can see all three peaks and also a coincidence peak of cobalt. Okay. I hope this much is clear. Yeah, you can see Compton peaks, backscattering peak. Yeah, every X-ray peaks I don't think so. X-ray peaks is not there. Yeah. Low energy. Yeah.
600 K.
X-ray peaks are not there. So I hope this much is clear. Now we will start with the task for the day. So I will give you,
In what cases then we go for sodium iodide?
if you want quick results, if you want
Then only identification if you want, then this is the
Pardon,
that
pardon?
peak.
only identification. For example, if you want to find out what is there. So if you want to check if there is cobalt, if there is cesium, if there is, or also sometimes we do calculation also in this, like most of us, because this is quite expensive. As Roy sir told, they are paying around 100,000 euros. It's almost like 10 crores or something like that for this HPG system. It is in Finland, but here it might be around 1 crore or something like more than 1 crore. More than 1 crore for this system. So it's not affordable for every laboratory to have it. So in that case, sodium iodide results from sodium iodide or also standard calibrated sodium iodide is acceptable. But the standard deviation would be very high, correct? How much standard deviation you give? Plus or minus 100 becquerel? Like 100 plus or minus 10%. Yeah, 10%, 15%. Here we are standard deviation is pretty low, less than 5%. Okay. So MDA formula you already know. Yeah, I had already explained. So using the background that you have already taken, you can calculate MDA. Okay. Yeah.
Calculating MD.
Okay.
Each element I calculate.
Yesterday you have gave the counting time of background as 60,000 seconds.
Yes.
And for sample it is 30,000.
Yes.
And what should we take as T? 60 or 30?
In that case, MDA should be calculated according to your sample time. Sample, yeah. So MDA, while we are calculating, we say that MDA is so much. Yes. MDA is so much. For so much, I had explained it clearly that it is for so much seconds. So we are saying for this much seconds and this much weight. That information should be clearly mentioned. Okay.
That is why we should take the sample count and background count in same time.
Yeah, maybe that is also done. Or else I can take MDA background by half.
Okay.
So background, so yeah, it is nothing but for 30,000 seconds.
Not linear all the time. That half value.
Approximately half,
Yes, approximately.
maybe 1 point or 2 point here and there. Does it matter? No. Okay, so we will start with the experiment. So for this batch, whether you want water sample or do you want swipe? Water sample. Okay. So if you want water sample, we will do it in this lab, this PC, and swipe samples we can do it in that PC. Okay, the data sheet that have been given to you right now contains some radionuclides. Okay, those radionuclides might be or might not be present in the sample. Okay, So first what you do is, first I'll give you QC sample, water sample. In that you identify the radionuclides and write it down in this table, and after identification write down the abundance, all those data, and write down the counts, calculate the efficiency. That whole activity might take today till evening. Okay, yeah. So next, tomorrow you can do the calibration, like activity identification. Okay, is that fine? Okay, so you can also, by doing this exercise, you can also compare the efficiency that you have got yesterday and efficiency that you are getting today, and you can compare them, like how different it is. It is widely different. So that is why all these things what we have, geometry is always important. Also, uh, in the yesterday's class, 3 different batches did efficiency in 3 different detectors, correct? And detector efficiency between 3 detectors is quite different, correct? So you might have observed that also. But if another batch has also done in these 3 different detectors, so you and the the guy who has done in the same detector should get similar values. So that also you can check. Okay. Now I will give you, I will check whether first I will give you the water samples here. If the other batch is not coming today, I will give you water samples in that sample. So I will divide you into 2. If the other batch is also coming today, then what we will do is that I will keep that as reserve for them. I'll ask them to calculate efficiency in that. Okay, that would be much better. Okay, so you can have your chairs around here. So do you want me to count these water sample and show you the spectrum live counting? Do you require that? Okay. So then I will keep the sample inside. Is that fine? Okay. Okay. Because I don't know. It is very sensitive. Okay. So this is sample to QC water. Now I have put a plastic, right? Yeah. Plastic ಒಳಗಡೆ ಏನಾದರೂ ಡಸ್ಟ್ ಇದ್ರೆ it will again affect. Plastic ಹೊರಗಡೆ ಡಸ್ಟ್ ಇದ್ರೂ it will affect. But this is a fresh plastic. Okay. So that is what I said. You always assume the sample is dusty. Always assume sample is dusty. Okay. So I'll just remove the air little bit. ಮೇಲ್ಗಡೆ ನೀಡು. Exactly.
ಇದಕ್ಕೆ ಟಿಶ್ಯೂ ಇಟ್ಟು
ಅದು just our precautions, so that we don't contaminate the detector. ಅದರ ಮೇಲೆ ಒಂದು ಕವರ್ ಇದೆ, ಅದರ ಮೇಲೆ ಟಿಶ್ಯೂ ಇದೆ, ಡಿಟೆಕ್ಟರ್ಗೆ ಸಪರೇಟ್ ಕವರಿಂಗ್ಸ್ ಇದೆ. But we are being extra cautious. Not just, see, it's, you might think that we are being over cautious, but if there is even a smallest leak, the whole setup has to be.
When we are taking the background, you are keeping that thing in on.
See, there are 2 types of backgrounds you can take. We keep empty detector. We don't keep anything. We don't keep the bottle. Otherwise, you can also keep the bottle to subtract the background that is coming from the bottle, from your container. That also is acceptable.
These bottles are glass bottles.
No, plastic.
Then it is fine, but because if you use glass bottles,
Then yes. Not only K40, I think some glass bottles, or the older ones, can have traces of uranium. So silicon, and some silicon may contain thorium. So those issues are there. So plastic, it's not a big issue. So now let me open.
You want the chair?
No, it's fine. So I'll start counting. Okay. So same thing, whatever you did right now. You want to do? Anyone?
Yes, sir.
Yeah. So the same thing you repeat?
Okay, first you want to clear all this thing.
Yeah. There is clear here.
Clear here only.
Yeah. And start.
time set.
Start only.
1 minute. Time set is
MCA.
required. We will do it for, I think 10,000. It is not enough, but we will do it. Yep.
Start acquiring.
Yeah, see, this counting is pretty slow. Still, there is no peak that is being developed. I think it will take at least, yeah, 2 hours. We have counted, I think, 60,000 seconds. 60,000. So you can see why we are giving you the already counted samples. So now I will open the file. Compare. Yes, so display, clear, ROS, clear all. So all the background, everything I have cleared. I've counted, the sample is counted for 60,000 seconds. It's up to you. Okay.
No, and background, like backside that is going on after counting.
Yeah, counting is going on. We can even shut down the PC and go home even the counting is going on. It will not affect the, yeah.
It will when you switch.
See, suppose so now it is counting is over here. Okay, I'll close. No, I have not stopped it. So here you can see that it is still acquiring. Acquire light is on. Okay, so that means even if I shut down, there is no effect to the detector counting
How
system.
do you open that one then?
Same way. It is still, it is just like how, see, it is something like there is already something playing on in your TV channel and you are just switching on that channel. So when I switch on that channel, I'll get this, whatever is happening over there, the program whichever is being run. No. It is background, it will be, unless I stop it, there is no problem. Display.
Previously analyzed.
Yes. So it's, the floor is for you.
Energy counter.
For your reference, I'll just share.
Here's the standard one.
Yeah. I'll just copy this sheet and I'll give it to you. No. ಅಲ್ಲಿ ಮೇಲೆ ಆಯ್ತಾ ನನಗೊಂದು ಒಂದೇ ಒಂದು ಕಾಪಿ ಬರುತ್ತೆ ಆಯ್ತು ತಗೊಳ್ಳಿ
You see, if you place the cursor at the peak, that is the importance of energy calibration. Place the cursor at the peak. It will give the energy. Then you look at the data. This energy corresponds to which one? measuring its energy, you can identify
As a big.
no, that is the quantum continuum for the one.
No, that is 49.
No. You take only very. Yeah, that is a good thing. Which one?
59.6.
Yes, yeah.
So note.
If it's not there, you write down.
You can note.
Just note down the energy.
It's almost source. It's almost
No, it has it.
Check everything.
Yes.
Now you do one thing, you find out the peaks that are present, and using LARA you find out which peak it is there. And then I will give you what is the activity of that peak. Okay?
So, first identify which are all the isotopes present.
ಸರ್ ಆಚೆ ಬೇಕು ಚೆನ್ನಾಗಿ ಬರ್ಲಿಕ್ಕೆ ಹೇಳೋದು, ಆಚೆ ಬೇಕು ಚೆನ್ನಾಗಿ ಬರ್ಲಿಕ್ಕೆ ಹೇಳೋದು.
ಅದು ಅವರಲ್ಲಿ ಹೋಗಿದ್ದಾರೆ
ಮೇಲೆ
ಯಾಕೆ?
ಗ್ರಾಸ್ ಕೌಂಟಿಂಗಿಗೆ.
ಅವ್ರು ಮುಗಿಸಿ ಬರಲಿ.
ಅಲ್ಲ, ಇದು 2 ದಿವಸ ತಗೊಳ್ಬೋದು ಸರ್. ಒಂದು ದಿವಸ ಎಫಿಷಿಯನ್ಸಿಗೆ, ಒಂದು ದಿವಸ ಆಕ್ಟಿವಿಟಿಗೆ. ಅವ್ರಿಗೆ ಇವತ್ತು ಬರೋದು, ನಾಳೆ ಬರೋದಿದ್ರೆ ಕಷ್ಟ ಆಗ್ಬೋದು.
ನಾಳೆ ಬರ್ತಾರಲ್ಲ.
ಅಲ್ಲ, ಇವತ್ತು ಬಂದು ಎಫಿಷಿಯನ್ಸಿ ತಗೊಂಡೋದ್ರೆ ನಾಳೆ ಅವರಿಗೆ ಆಕ್ಟಿವಿಟಿ ಕ್ಯಾಲ್ಕುಲೇಟ್. 5 ಸ್ಯಾಂಪಲ್ ಅಲ್ಲಿ ಕಷ್ಟ ಇಲ್ಲ, 5 ಸ್ಯಾಂಪಲ್ ರಫ್ ಆಗ್ತದೆ. ಇದು ಸ್ವಲ್ಪ ಕಷ್ಟ ಉಂಟು. ಏಕೆ? and they will analyze the activity in this water sample. That they have tried it.
Varium 130, varium yes, varium 133 M.
No. I think it should be anthropogenic. Natural, not much.
If this, okay,
Right now, let them use Lara. It's better to use EML, I guess.
it's all the field, when you have to calculate the activity. Then you have the coefficient of it's easy to.
Yeah.
Cannot touch.
Yes.
Quite straightforward calculation.
Yes.
If you are using efficiency, very easy.
Let them do the hard. If you do just efficient answer, you might not understand the nuances in calculation. One batch is copying the gross, or this is the gross architecture, the calculate the background, then they
I only done this. Let's start from here.
Varium 133 I feel actually.
Can we start from here? Okay. Controller.
Control. This is controller.
Where is control?
It may not be
Controller. Same line it should be.
If we talk of varium 133, which is there for 356, so it is also it will be there. No, maybe yes. Okay. Yes, is also
Sir, right, sir.
384 is also same varium.
384.
Fine, is 384.
you see varium 133. Yes, the gamma piece.
Now we have to come to abundance.
Anyway, you need to write it abundance in the next table. I feel it.
I think we should write Varsha 10.
Varium 133, madam.
303 is varium.
That's from Lara.
Yes.
Same, ma'am.
302
The 303 is also varium.
So many variant.
Yeah, ma'am.
Of course, what?
Then 380.
302.
302.
Five elements are varium. 5 elements are varium.
Yes, the one set is there. We should see individual
Three,
evidence.
which is also variant. That's 302.
Yeah, 380 is there. You see the individual abundances, you will understand it. Individual isotope చూడండి abundances అలా.
So 1, 2, 3, 4, 5. I don't even consider.
ఏ వాల్యూ సి వాల్యూ
How much by abundances they are getting individually. Variable is.
Then for 276.3 is 7.13. Does that M play a role or meta stable? It has to be met, then you cannot take this.
It is written here. It is written here. Why when you are talking about remaining values, now one can be
18.31. 356.
Control L.
Already.
format will be 100%. That's 99 point something. I think you check this.
This is so good.
Yeah.
That means this is channel. For which channel is
982.
An average should be 40.
Already 35.
Okay, done.
Yes, we got ammunition.
Barium.
Varium.
One not.
4.
Activity.
Yes.
How much is the value?
104
0.04
becquerel per kg. Barium is 17.5 becquerel per kg.
Which is also
So many.
How to figure out? Barium is 17.5 becquerel. Cobalt is 19.4 becquerel per kg. Cesium is 76.9 becquerel per kg. 76. And the reference date is 2011. 1/1/2024. I don't know. It's up to you. 76.9. 1/2024. It's 1/1/2024 CGM.
One verify the information.
Today.
Can you see the date on that file?
Just said now. So that
Normal
means, but
laboratory.
see this 17.5, this one not so.
Area.
25, 2024. 25, 2024.
Okay. You got it. Then from
Yeah,
first
that's
step.
it.
Hello, 25, 2024.
5 months.
Oh, that is reference. 25, 24 is the and 64 Amrshin 241. Area. 20.
Plus or minus.
20896.
96
Plus or minus 896. 896. Plus or minus 0.8.
In this, there is no need of taking for the standard deviation.
The standard, as it is a standard.
So no need of
So need
changing, so
checking.
don't write.
661.
661.
661.
My age.
No, I need.
It's yours. Avanes, it's not a problem for me.
Days will change.
Eighty-one point one area. 2,888. 2,888.
830 million.
So, what do you suggest the discussion? I have established this.
Time use.
Sample temperature, what is that of reasons?
Now we told 60,000.
30,000.
There can be some more.
I should see the results, but
Yeah. What is the energy?
276, right?
276.3.
294.
That is
294.
294.
so there are
Very less than
No, I haven't.
ways to discuss or conclude. Is it related on the measurement system itself? Or should it be
that. Controller.
What's the material? It's soil. Yes. Soil to yeah. That's all physical parameters.
845. Area for 845.
Okay. That is 56. I hope I understand what you are doing. It's not a rocket science. 394. 394.
394. Left is selected. Sometimes controller.
Same line. It should come in the same line. That's what they were.
But there is no any spot.
390.
390. 390. It's just 16.
Sarita. Nuclear physics Nagaraju.
Fine. Now, this is 3. Nine nine two zero.
One second. 117. One double 6 8. The review is on 20. 1
1505.
That's
Background.
next background. We are supposed to save this.
Save this.
Save this.
No.
555.
She's changing the 990. Select it just for shortly. selected is it.
So now here we calculate for
How do we
Display.
ROIs.
Open
T half
database, file back.
Yes.
Back.
Okay, back. So we calculate that by 0.6.
Background check.
Timing is different.
background is 40,000?
40,000.
Check in. Count in the
And then number of users that times
It is coming.
It's already there.
This is for one.
you need to put the
Keep the cursor over there.
P51.7. 1850.
1850. That's why we omitted
It's not a
that.
fingerprint for nuclear. Light is coming so that the lead to 1,4.
Network project होने में
Yes, 290. Yes,
it's not like not the this really.
No, I don't know how to write it.
462 462. Nine 963.9.
It will not move.
I will not name it as a here only two ranges.
And then what the are you? Yes, we want
And
all
I know
three.
this number is
Then
already
you
changed.
take
In 75.
10.
yes, is it?
What is the last name?
1407.
Date.
1407.
1407.
Nothing is there.
One 763.8.
05.
Then also it is very less.
These are not fixed. No, the work has been done. Okay. Done. Measurement these $500 gram. Date?
500
Date gram. Date it is
500 gram.
Yeah.
Ah, so, right.
So date is one.
You have to see the
Thank you.
back. Only we have to check background for this.
It was.
ROI
You have not
submission.
ROI sir. Might be zero, but still you have
Yeah.
to do it. The practice should be done.
Last two, one.
No, no. I want to know.
Students, both sample and same.
keV. What is keV? 6967. 0.6 40. In this. 573. 457. 24.77, 120. 445. 0.1. 10. 4. 8. 1. 434. Yes. 462.
So we have seen.
0.7.
Take your അടുത്തേക്കെങ്കിലും വരുമ്പോൾ no, you can go and come back. So I will give them that piece. No, you can come back in another 5 to 10 minutes. By the time I'll explain them what we were doing right now. Okay. So, I think you have seen how an alpha spectrometer works, how alpha counter works. You have taken the activity. All that exercise is done right now. Right. So yesterday we have seen spectrum of lithium and cobalt in the day before yesterday or yesterday. I guess.
It was not for stable, it was for
HPG, yes. Yeah. So we had seen the cesium and cobalt 60 activity, but we have not seen how the same peak look in a sodium iodide detector, right? So initially I start with that the exercise in sodium iodide detector. Then we have an exercise for you that, as discussed, we have got some samples from the International Atomic Energy Agency for the inter-comparison exercise. This exercise is being held yearly. Every year they send us samples and we give them results, and only if our results are acceptable, only then we can say that our results are valid. So this is being held with 300 plus labs around the world. So we are happy to say that we have got all our results as acceptable, and and that has not been the case this year, but that has been the case from last 10 or 15 years. But for last 5 years I have been doing that, and we have been able to get acceptable results in the last 5 years. But even before that, the same trend has been continuing. So we will also give you that sample, and we will show you how the format is, how the results come, how they give us samples, and how we have to analyze it. Okay. Initially we'll see that how the spectrum for cobalt and cesium looks in a sodium iodide detector. So this exercise, what you are doing today, might take 2 days. Today you can take the efficiency and plot the efficiency graph. Tomorrow you can take the activity and calculate the activity of the sample. So since it's already 4 o'clock, right? So by 5:30 we can finish taking the efficiency values and plot it, and tomorrow we can take the readings for activity. So after this exercise, you will be more confident on analyzing this, analyzing any samples for in high purity germanium detector and also sodium iodide detector. Okay. So this is just a demonstration on how the cesium and cobalt peaks look in a sodium iodide detector. So I keep the samples inside. Let us see what happens if I put both the samples. What would be the conclusion? Cobalt has 2 peaks. I hope you can see the peaks. How many peaks should we get? 3 or more?
More than 3.
What is the 4th peak then?
Alienation peak is also there.
Some peak. Some peak should also. So you can see that here we are getting the cesium peak. Getting 1175 and 133. Have both the peaks here, 1332. Okay, and some peak would appear somewhere over here at 2500. Yeah.
Coincidence.
Okay. Coincidence, yeah, that's a coincidence. And there is one component like this. So, can you see the difference between HPG and sodium iodide? The main difference over here is the channel difference. So, the resolution was so good that I had used 660, 655, 658 proper peak, correct? Here you can see that my left marker is at 742. So any peak that comes between that. So if there is a, let us say, if there is a radium source which gives bismuth at 609, that peak will not be detected if cesium is also present in this sample. Similarly, 795 peak of bismuth, and 795 you also get a cesium 134 peak. So if you have cesium 137 and 134, again that is not resolved properly in this peak. Again here you can see that cobalt peak was very wide in the HPG, that the 2 peaks were well resolved, correct? Here you can see that both the peaks are adjacent to each other. There is no much not a problem. The counting is where one peak ends, the second peak immediately starts, and it is not well resolved. So this is the basic difference between a sodium iodide and HPC. I hope this is clear, right? Any doubts here? No, it's actually there is an issue with this. This is not closing, so we are trying to close it. Once it closes, it should actually come a little bit down. I'll stop the counting of the spectrum. can put, but what is the use? Yeah, we can put. We can get, if you put thorium, you get more peaks than one. Yeah. So we get a spectrum of peaks. So now, coming back to the topic, so can you give me that sheet? The first one. No, not this. So during intercomparison exercise, we get an email or a printed, priorly we should get a printed copy about a sheet like this, which says IAEA TRC 2024-1 Worldwide Proficiency Test Exercise, Determination of Anthropogenic and Natural Radionuclides. So this year, the first page you will get the description of samples. So you can see there is a spiked water, 1 and sample 1 and 2, and a spiked water, where sample 2 is quality control sample. 3, 4, one is sediment, and another is bauxite. And 5, 6, 7, 8, as discussed earlier, are swipe samples. Sample number 5 is our sample that has to be analyzed. 6 and 7 are QC, 1 QC for cesium, 1 QC for strontium, and 8 is a blank sample. Okay, so this is the sample description, and we have to analyze. They have given the sample 2 concentration of values in sample 2. Here they have given concentration of sample radionuclides in sample 6 and 7, and they have asked us to how to handle these samples and choice of methods, and they have given us a deadline. Before this we have to submit. And the reference of for decay correction in all the samples is 1/1/2024, January 1, 2024. So that is what the reference date is. Now, how do we report it? So sample 1 has to be reported in becquerel per kg. If we analyze by ICP-MS, we have to analyze. We have to report it in nanogram per gram. Okay, per 1 gram of sample. And then sample 3 is gamma ray emitting radionuclides. Sample 4 again gamma ray emitting radionuclides in becquerel per kg. Sample 5 we have to give it in becquerel per sample. So this is the units that they have given, and some more additional information. So if you get accepted, there is no good, better, best here. You have either accepted, not accepted, and warning. So you have to calculate. They will calculate precision and accuracy. If both precision and accuracy is accepted, your sample is accepted. If both are not accepted, your value is varying a lot. It is not accepted. Warning is when precision trueness rating is accepted, but precision is not accepted. Okay. Yeah, so that's it. So if this is clear, shall we analyze a sample? Okay. So you can all turn around this detector over here. Here. I will not show you. Do you want a sample that is counted previously, or do you want to freshly count the sample? So if you count freshly, it will take 2 days. 1 day for QC correction, 1 day for sample counting. So what to do? We have already have a spectrum. We will show you that. You can calculate, because this takes quite a long time for the spectrum to develop. So we had kept a sample over there. It has not even developed properly. So it will take time. Okay. So first I will give you the QC of water sample. Do you want to analyze water or? Now it is your duty to identify what are the samples that you have identified. Okay. Then I will give you the activity values for these radionuclides, and then you can continue in calculation of the uh, area under the spectrum. First, to identify the radionuclides that present in the spectrum, identify the radionuclides. Then quantify, then count the radionuclides, the whatever the counts that you're getting. Then calculate the efficiency. This much work you have to do today. So you can start. So keep a chair here. It comes here, this detector. You can take a chair from the lab. Just keep it here so that you don't take. So just, you can now come closer. Start working on this. Take your chairs and so last you have which one? Unknown sample.
We don't have to clear the
No. So if you take background, you no, you can all sit so that everyone can see you. Please sit down. No, I don't want to. No, they will leave now. Theirs almost is done. Cable is play. So everyone who is using the PC, please sit down so that people behind you can see. Okay. So you can take a couple of chairs here and sit down. Those who are standing can stand in the back.
Decimal term to find E to here and E to here. Decrease. One rule is there.
Now it's like this.
This is the main line. Because this is the main line.
What is the alpha spectrometer used? Name of the spectrometer. It's a Miriam, the company is Miriam.
think that is also again we need people can come here.
What are some Excel something?
4810.
Yeah. Standard. Yes. It's like end to tail. That is same. 59 as well as same. What as well as first year code? Yes, ma'am.
സംശയം നമുക്ക് ആ സ്റ്റാൻഡേർഡിൻ്റെ വാല്യൂസ് തന്നു ഞങ്ങളത് നോട്ട് ചെയ്തു അത് നമുക്ക് എഫിഷ്യൻസി പേപ്പർ എന്നിട്ട് ഉണ്ടോണ്ടെങ്കിൽ തന്നു അത് വെച്ചിട്ട് ഞങ്ങളെടുത്തു എന്നിട്ട് അത് ആ എഫിഷ്യൻസി ഗ്രാഫിൽ നിന്ന് അതിൻ്റെ അതിൻ്റെ ആക്ടിവിറ്റിയാണ്
Overlap. 454. Sample of data.